Welcome to the Using the DDS and FIR compiler IPs with the AMD Kria KD240 Drive Starter Kit demonstration. We'll start with an overview of the AMD Kria KD240 Drive Starter Kit and the basics of the DDS and FIR compiler IPs. Next, we'll explain the design flow process, including block design creation and validation, bitstream generation, and exporting the XSA from the AMD Vivado Design Suite. Then, we'll show you how to create a Vitis platform using the exported XSA and how to program the programmable logic with the bitstream. Finally, we'll show how to access the ILA from the hardware manager of the Vivado IDE. To get started, you'll need the Kria KD240 Drive Starter Kit, which includes the K24 SOM, a carrier card, and a thermal solution. In addition, you'll need the power supply and adapter, micro SD card, and Ethernet and micro USB to USB-A cables that come with the kit. You'll also need the AMD Vivado Design Suite and AMD Vitis Unified IDE installed on an Ubuntu host machine. The AMD Kria KD240 Drive Starter Kit is an evaluation platform for the K24 SOM focused on motor control and power conversion applications. The KD240 and its base K24 SOM support full user customization through the AMD Vitis Unified IDE, customizable acceleration overlays, and AMD Vivado Design Suite hardware board files. The integrated combination of hardware, platform, and software provides a quick out-of-the-box experience for developers that can be leveraged for product designs. The AMD Vivado Integrated Design Environment offers an intuitive graphical user interface for visualizing and interacting with FPGA designs. This interface allows you to assemble, implement, and validate your design and intellectual property, IP. The design used in this demo will utilize two specific IP blocks from the Vivado IP catalog: the DDS compiler IP and the FIR compiler IP. The AMD DDS compiler IP creates a customizable direct digital synthesizer. A DDS uses a lookup table for sine wave values. It takes a phase increment as input and outputs the corresponding sine wave data point. This input value controls the output frequency. A smaller value translates to a slower step through the table and a lower frequency, while a higher value results in a faster step and a higher frequency. In this demo, we'll be using the DDS compiler IP to generate a chirp signal to validate and verify the functionality of the FIR filters. With regards to the AMD FIR compiler IP, it is a configurable FIR filter that allows a user to simply specify the filter coefficients and hardware parameters, such as coefficient width and sampling frequency. The configuration window of the FIR compiler IP also shows a frequency response plot of the filter with the given coefficient set and configuration parameters for extra verification. In this demo, we'll be testing three FIR filters with different frequency responses, low pass, band pass, and high pass, by using the same chirp signal to show how quickly a DSP design cycle can be implemented in behavioral simulation and validated on the KD240 starter kit. The DDS and FIR compiler IPs are found in the AMD Vivado Design Suite. Launch the Vivado IDE by opening a Linux terminal window and entering the commands to source the Vivado tools. Type Vivado in the terminal to launch the Vivado Design Suite. The tool opens with a welcome window. From here, you can create a new project, open an existing project, enter TCL commands, and access documentation and examples. Click Create Project to begin the process. This will launch the Project Creation Wizard. The Project Creation Wizard allows you to set the project name, location, and project type, RTL or post-synthesis. In the Target Device Platform selection, switch to the Boards tab and type Kria in the search bar. Click the row for Creo KD240 Drive Starter to select it, and then click the Connections hyperlink. This opens the Manage Board Connections window for selecting how the K24 SOM is to be connected to the KD240 carrier board. Select Drive Starter Kit Carrier, SOM 241, for Connector 1 on K24 SOM, SOM 241, and Drive Starter Kit Carrier, SOM 42, for Connector 2 on K24 SOM, SOM 42, and click OK. Click Next to advance to the summary. Click Finish to accept these settings and build the project. Now that the Vivado Design Suite project has been created, we will create and add a block design to the project. We will use the IP Integrator tool to manipulate this block design. The Vivado IP Integrator is a graphical tool that assists with stitching together various pieces of IP. Click Create Block Design from the Flow Navigator and give it a desired name. The IP Integrator workspace opens with a note in the Canvas area inviting us to begin adding IP. Click the Add IP icon in either the middle of the canvas or in the toolbar. Enter Zinc in the search field to narrow the search parameters. Double-click Zinc UltraScale Plus MPSoC to add the processing system block to the design. A green banner will appear at the top of the diagram window with the option to run block automation. This option instructs the Vivado Design Suite to automatically configure the Zinc UltraScale Plus MPSoC IP for the Creo KD240 board based on the selected project preset files. Click the Run Block Automation link. This opens a Run Block Automation dialog box that lists all the IPs currently in the design eligible for block automation. Ensure that the Apply Board Preset option is selected and click OK to run the block automation. Once block automation is completed, add a Processor System Reset IP. This IP controls the timing of the reset signal that is sent to the programmable logic of the Creo K24 SOM. Connect the slowest sync clock input of the processor system reset to the PL clock 0 from the Zinc UltraScale Plus MPSoC. Then connect EXT reset in of the processor system reset to PL reset 0 from the Zinc UltraScale Plus MPSoC. Finally, connect PL clock 0 to max IHPM 0 FPD-A clock and PL clock 1 to max IHPM 1 FPD-A clock. With this basic block design created, a top-level HDL wrapper to instantiate the block design in the project can be created. Right-click the block design under the Design Sources node and select Create HDL Wrapper to begin the wrapper creation process. Keep the default option and click OK. The Vivado Design Suite will then generate the HDL top-level wrapper file and set it as the top file in the project. Next, add the DDS compiler IP to the design by clicking the plus button. In the search bar of the window that appears, type DDS. Double-click DDS compiler from the list to add it to the block design. Configure the DDS compiler IP with the following settings. In the Configuration tab, select Hardware Parameters in the Parameter Selection section. Set the phase width to 32 and the output width to 16. In the Implementation tab, set the phase increment programmability to streaming and the phase offset programmability to none. Set the output selection to either sine or cosine. Under the Detailed Implementation section, select the Packet Framing for Data has TLAST option. Additionally, check the box for A reset N to create a reset port on the DDS compiler and the box for Output T-Ready. Click OK. Since we'll be using the same chirp signal for all three FIR filters, low pass, LPF, band pass, BPF, and high pass, HPF, let's create two copies of this now configured DDS compiler IP. Right-click the existing DDS compiler block in the design and select Copy. Paste the copied block twice in the design window to create two additional DDS compiler IPs. Now we'll add a simple state machine. This state machine will stream the phase increment values to the input of a DDS compiler block. The main functionality of this FSM is to handle the timing of when to increment the phase increment value and the AXI stream interface signal handshaking. Since this is custom HDL you will add to the block design, the source file first needs to be created or added to the Vivado project and then added as a module to the block design. Click Add Sources from the Flow Navigator. Select Add or Create Design Sources and click Next. Click Add Files and select the source file. Click Finish to add the source file to the project. Once the RTL source file has been added to the Vivado project, go to the diagram window of the block design and right-click anywhere in the blank space. Select Add Modules. Select the Phase Increment State Machine module and click OK. Repeat 2 more times to add one for each of the other DDS compilers. Connect the phase increment output to the input of the DDS compilers. Connect all the clock signals to PL clock 0 and all the reset signals to peripheral A reset N of the processor system reset IP. With the DDS compilers in place, along with the phase increment state machines to control them, the next step is to add the FIR compiler IPs for each of the target FIR filters. Click the plus button and search for FIR in the window that appears. Double-click FIR compiler from the list to add it to the block design. Configure the FIR compiler IP block with the following settings. Under the Channel Specification tab, change the input sampling frequency to 100 MHz. Also change the clock frequency to 100 MHz since the clock driving the FIR compiler IP, PL clock 0, is 100 MHz. In the Implementation tab, change quantization to quantize only and coefficient fractional bits to 2. Click OK to save and close the FIR's configuration window. Copy and paste the FIR compiler IP to create 2 more instances. Connect the MAXIS data output of each DDS compiler to the SAXIS data input of each respective FIR compiler. Also connect each input clock of the FIR compilers to PL clock 0. Double-click an FIR compiler. In the Filter Options tab, set Select Source to be COE file and then browse and select the COE file. Repeat this process for the other FIR compilers. While most of the design is complete, you will now add integrated logic analyzers to view the data flow going in and out of the FIR filters. This will be useful when the bitstream is running on the PL of the KD240 starter kit. Click the plus button and search for ILA in the window that appears. Double-click System ILA from the list to add it to the block design. Configure the System ILA IP block with the following settings. Under the General Options tab, change the number of interface slots to 4. Under the Interface Options tab, change the interface type to AXIS for all 4 interfaces and click OK. Right-click the desired signal lines, such as the FIR filter inputs or outputs that you want to add the ILA to, and select Debug. Click the Run Connection Automation option that will appear in the green banner. In the Connection Automation window, check the box to enable each signal you want to monitor. Additionally, enable the option for AXI Stream Protocol Checker, since there is an AXI interface between each IP block. Click OK to run the connection automation. Validate the block design to ensure that there are no errors or critical warnings. Select Tools, Validate Design. If no issues are found, a dialog box will appear that reports that validation succeeded. Save the block design. As an initial functionality check that takes less time than generating a bit stream and running it on hardware, a behavioral simulation will show the FIRs in action. Let's now perform this behavioral simulation. Click Add Sources from the Flow Navigator. Select Add or Create Simulation Sources, and then add the test bench file by browsing to the proper location. Click Finish to add it. The test bench file will appear in the Sources window under Simulation Sources. Right-click the test bench file and select Set as Top for the simulation sources. Click Run Simulation and select Run Behavioral Simulation. Once the simulation has launched, go to the Scope tab and add each desired signal to the waveform window that you added to the ILA in the block design. Change the radix of the target signals from the DDS and FIR IPs to signed decimal and the waveform style to analog. Specify a time to run the design for. In this design, 100 microseconds will capture a sufficient amount of data. Click the Run to Time icon. Zoom in on the waveform window. Here you can see the clock and reset signal alongside the top waveform, which is the first DDS compiler output. The chirp signal is the same for all three. Below it, the first FIR output, the LPF, is displayed, followed by the BPF from the second FIR and the HPF from the third FIR output. With the FIR filters validated from a behavioral perspective, they're ready to run on hardware. Click Generate Bitstream from the Flow Navigator. The Launch Runs dialog box appears. Leave the settings at their default values and click OK to launch the generation process, which may take several minutes. Once a bitstream has been successfully generated, export the hardware, including the bitstream, in the AMD compressed XSA file format. Select File, Export, Export Hardware. The Export Hardware Platform dialog box opens. Click Next to proceed. Select Include Bitstream. Choose a file name and path for the XSA file. Click Finish to export the hardware. This will create a file containing a description of the hardware and the included bitstream at the specified location. This completes the hardware design process using the Vivado IDE. Even though the design is purely RTL, the Zynq UltraScale Plus MPSoC processing system requires initialization and booting within FSBL and U-Boot before the programmable logic can access any clock to run. Hence, to achieve the minimum boot requirements, we will create a platform component based on the generated XSA and an application component on top of that in the Vitis Unified IDE. We will then program the PL with the bitstream so that the design will be running and the ILA can be accessed from the hardware manager in the Vivado IDE. Launch the Vitis Unified IDE from the Vivado IDE or the command line. Create a new workspace by selecting Open Workspace from the Vitis Components tab. Select the desired location and click OK. The first step is to create a platform component. This component reads the exported XSA file from the Vivado Design Suite and creates connections to the hardware design, including the board support package and boot components. Select Create Platform Component from the Vitis Components tab. Name the platform and point it to the location of the XSA file that was exported from the Vivado Design Suite. Give the OS and Processor page a few moments to read the XSA. Default options will be populated, which we can modify. Be sure to select Standalone for the operating system, PSU Cortex-A530 for the processor, and enable the options to generate boot artifacts and PMU firmware. Click Finish and wait for the platform component to generate. The AMD Kria KD240 SOM utilizes both UART ports, UART 0 and UART 1, in its Zynq UltraScale Plus MPSoC's MIO. However, UART 1 is the default JTAG or UART serial ports, while the hardware BSP in the platform component defaults to UART 0. This means that any print statements in our code will be sent to UART 0. To update the BSP, open vitiscomp.json in the Settings folder of the platform component. Navigate to PSU Cortex-A530, Standalone PSU Cortex-A530, Board Support Package Standalone, and change both Standalone STD in and Standalone STD out to PSU UART 1. Do the same for the FSBL under PSU Cortex-A530, Zynq MP FSBL, Board Support Package Standalone. Build the platform component by clicking Build from the Flow tab. A green check will appear when the build is successful. After the platform component is built, the next step is to create an application component for a standalone application. To create an application from the Hello World template, select Create Application Component under Examples in the Welcome tab. Select the platform component created earlier. As the platform component only has one standalone domain for the first A53 core, it's the only option for building an application. Finally, review the selections and click Finish to generate the application component. Again, run an initial build on the code as is before customizing it. Connect the KD240 to the host PC and power on the board before launching the debug run. Select the target application from the component drop-down list in the Flow window and then click Debug. This will switch the IDE to the debug view, boot the target board, launch the application, and stop at an automatic breakpoint at the first line of the main function. This performs the minimum boot sequence required for the Zynq UltraScale Plus MPSoC, allowing the AMD Vitis Unified IDE to program the PL with the bitstream. Consequently, the design will be running and the ILA can be accessed from the hardware manager in the Vivado IDE. With the Zynq UltraScale Plus MPSoC booted and running, switch back to the Vivado IDE and launch Hardware Manager from the Flow Navigator. The bitstream doesn't need to be reprogrammed as it's already loaded on the device. Since the design is free-running in the PL, simply run the ILA to see the waveforms from the DDS and FIR compiler IPs. Note that you may sometimes encounter issues accessing ILA waveforms from the Vivado Hardware Manager. In such cases, you can refer to the reference waveform shown here. This verifies the FIR functionality both in simulation and on hardware. So, the key takeaways from this demo are: The AMD Kria KD240 Drive Starter Kit and its base K24 SOM support full user customization through the AMD Vitis Unified IDE, customizable acceleration overlays, and AMD Vivado Design Suite hardware board files. The DDS and FIR compiler IPs simplify the design process. With the DDS, you can generate chirp signals for FIR filter validation, and the FIR filter requires only coefficient and hardware parameter specification. Finally, the AMD Vivado Design Suite provides an intuitive GUI for visualizing, assembling, implementing, and validating FPGA designs and IP. To summarize, in this demo you gained an overview of the KD240 Drive Starter Kit and were introduced to the basics of DDS and FIR compiler IPs. You learned how to create a block design, generate a bit stream, and export the XSA file. You then saw how to use the XSA for platform creation, program the PL with the bit stream, and access the ILA block from the Vivado IDE hardware manager. Thank you for watching.